So without further ado, let's get started. So like I said, we're going to do chapters 1 through 6 right now. So our first chapter was lesson 1 all the way back in the beginning of the semester. So this was just kind of setting up about different variables and kind of like what samples and what populations are. So won't spend too much time on this because I'm sure you guys have some sort of idea of what samples and populations are. So just remember our populations are going to be our entire group that we have, and then our samples are what we take from the population. And our samples are actually where we collect the data because, it's obviously very hard to get data from the entire population because we don't necessarily have, it's hard to get all those people or the entire group that you're looking at. So what we do take is samples from the population, and parameters and statistics are just the measurements of the different ones. So parameters are the measurement of populations, and then our statistics are measurements of our sample. So from our population, we do take samples here, and then this point down here is important. We use our samples to make inferences about our population. So our final conclusion our inference is going to be in terms of the population. So depending on what we find, we are going to make that inference about the population. Our sample is used to find that. So remember, when we get into our hypothesis test, we always say things such as, we're going to fail to reject, the null or whatnot, and then it's in terms of the population. So keep that in mind, that all the inferences that we make at the end are about our population. We're just using our samples to find it. All right. Okay, so variables, if you guys remember, these are literally just talking about the different variables that we use in statistics. So firstly, we do have explanatory variables, which are independent variables, and they explain the response variable, which is the dependent one. So that's kind of all that is. It's just talking about the two different types that you have. The response variable does rely on the explanatory variable, and it's affected by that. So if the explanatory variable does change, our response variable will change as well. Yeah, just want to make sure there's nothing else. Oh, and keep in mind that for response variables, if we do have something, so remember, independent and dependent, just to kind of go over the definitions of that. Independent means they're, unrelated in any way, and then it's usually in a randomized experiment because that's how we are able to get a representative sample. And then if something's dependent, we often have paired or match paired variables, and that means that they're going to be the same. They're often the same in both groups, and that shows that they are dependent on each other. So yeah, that's that. All right. Okay, so different sampling methods. We do have, if you guys remember, a simple random sampling, which is basically us just taking a bunch of samples from our population, and it is probability based in terms of the fact that we're trying to find, the probability of them coming out of the population. So when we do this, we are doing it without replacement. So an equal chance of selection just means that if you're taking samples, you are going to have, a 40% chance or something of getting that sample every time. So in simple random sampling does give us a representative sample, which is what we want because that's going to represent our population. And then convenience sampling is basically when you do this is like when you don't have access to the entire population. So this isn't really good because you can't have sampling bias because for example, if you're trying to find information about all Penn State students, but all you have access to is your one class, that may give you some type of biased results there. So it can favor certain outcomes. It's not random, but it's something that is easy to do, which is why some people do it. But you shouldn't. Okay. So different types of studies. Remember, we have experimental and observational. So experimental are the ones where the researcher does impose some sort of treatment. They're making a change to the sample there. Yes, this presentation is being recorded. So you can go back and and it's on the YouTube channel. If you know where that is, on the Review Session Central page. If you don't have that, I can copy and paste the link in there for you. But yeah, try to, oh wait, if you can't hear me, I guess, let me, yes, I'm okay, yes. So, but anyway, so yeah, experimental. So that's going to be when we're taking a bunch of random samples, then too, controlling for those confounding variables, which is going to be, confounding variables are the variables that are kind of like a third variable that are affecting your results, but it's not really what we want. It's affecting the true results. So, so yeah, then we have our, we can have a control group or blinding in our experimental groups or experimental studies. So control group is kind of the one that's going to say, we can compare it to and say, if there was no treatment, we can compare it to and say where that, what the difference of that is. Blinding is talking about, if the researcher or the subjects or both of them know what type of treatment is being, is or is not being imposed on them. And then observational studies, this is kind of comparing the same thing between like simple random sampling and convenience sampling. So observational, there's no manipulation. You literally just are watching, I liken it to people watching. So you're just kind of checking out the situation and taking data dependent on that. And you can't have confounding variables in here because you're not controlling for anything and they're not randomized. You're not taking random observations. It doesn't really work. So observational studies are not as representative of our population, so we do always try to have our experimental studies there. Okay, yay, let's try a review question. So like I said, we'll have review questions throughout, so please go ahead and participate in these. I'll go ahead and read the question, and you guys can check out the answers and type it into the chat box, and we will go over it together. So let's try this first one. So we have a research question that is asking, can the age of a child in months be used to predict his or her vocabulary? So in this case, we're trying to find out, so data were collected from a sample of 500 children. 39% of the children between 40 and 60 months had an above average vocabulary. I always wonder why people, say that's how old their children are, just say they're like 3 years old. But anyway, so which set of answers lists the response variable, the explanatory variable, and the sample statistic in that order? So go ahead and read through these options down here, A through D. Type your answer into the chat box, and we will go over it together then. And if you don't know, say I don't know, or just don't. So yeah, we'll go over it together then. Okay, great job, guys. Yeah, so let's go over this one. So let's just kind of review what the different types of variables are. So remember, our response variable is dependent upon our explanatory variable. And then our explanatory variable, remember, is independent, so it's not affected by anything. And then our sample statistic is coming from our population. So what we want to look at, so we had our data collected, and we're trying to see the age of the child being used to predict the vocabulary. So whenever you see predict, you can often assume that the first one is our, so we're checking if the age of the child can be used to predict their vocabulary. So we're using that age to predict the vocabulary. So if the age changes, then the vocabulary is going to be our vocabulary is going to change. So remember, so that means that our vocabulary is our response because it's dependent on, is going to be dependent on the age in months. So how old they are is going to explain their vocabulary level. So that's why our answer here is actually going to be D, because our age in months explains our vocabulary, the amount of what type of vocabulary they have there. And then our sample statistic is going to be 39%, because we are talking about a percent here in terms of what percent of that population or of that sample. So our sample size is actually this 500. So that's why we can cancel out A and B immediately, because that is not our sample statistic. So being between C and D, we do want to make sure that we're talking about. So our response variable would be first. So our vocabulary is dependent on our age and month. So C isn't correct because our age isn't dependent on the vocabulary. Like someone's vocabulary doesn't explain how old they are. So if vocabulary changed, it's not gonna, the age isn't gonna change. That doesn't make sense. So our vocabulary is the response dependent on our age and months. So, and then our sample statistic is 39%. So our answer is D there. Does that make sense to everybody? Any questions on that one? That's okay if not. I'm just checking. But yeah, okay, great. So let's keep cruising then. All right, so good job, guys. So let's do another review here for these chapters. So which of the following is true about the population mean and the sample mean? So read through A through D and then let me know what you think the answer is, and we will go over this together then. All right, perfect. Good job. So here our answer, I lost my pen. Oh, here it is. Okay, so our answer here is going to be D, because remember, our population is static, so that doesn't change. That's always going to stay the same. So because if it changed, then our samples would be, they wouldn't be represented because they would keep changing as well. Our sample is what varies. So our sample varies. So the answer would be D here because values of the sample mean will vary according to the sampling distribution of the sample mean. A is not correct because it's saying that the values of the population mean will vary, which is not true because, like I said, they don't change. And then B is also not true because it says the same thing, that values of the population vary. It's saying both of them do. So that's not true as well. And then C, once again, says value of the population mean will vary, which is also not true. So D is the answer there because our sample is the one that that varies. So good job. I think I spelled varies wrong, but that's okay. Okay, great. And like I said, stop me if you have any questions on any of these. More than happy to answer any clarifying questions. And one tip I have for throughout the review, if you are if you're going through and you realize like, oh, I really need to work on this chapter, I forget about this, make notes, and go through and say, like, oh, chapter 1, population, that was something I need to work on. And then you can, so that it kind of guides your studying. And you can obviously go back to this review, but also the reviews specifically for the chapters that are on the YouTube channel. So those are going to be the reviews that are specific to that chapter. So they're a little bit more in depth there. All right, yay, we're already on chapters 2 and 3. So we talked about, the variables and the different types of like experiments we can do with them. So now we're going to talk about different types of variables. So we do have categorical and quantitative. So categorical are going to be our different labels, obviously, categories, that's why they're called categorical. So these are going to be things like colors, flavors of something, a brand of something. And then we do have nominal and ordinal. So nominal is just saying that there's no order for these. So these would be things like flavors would be something, there's no hierarchy. And then ordinal is going to say that there is a hierarchy. So these would be things like class standings, freshman, sophomore, junior, senior. They do have some sort of order, but they are also categories. So those would be ordinal variables. Quantitative, they always have numbers. They have values associated with them. And obviously they're always going to have a meaningful order because, 1 always comes before 60. And then discrete means that they take on a set number of values. You can't, split them up. So if you're talking about number of raccoons or something, not sure where I came up with that one, but if you're talking about that, you can't really say like 1.645, you can't, that's going to be discrete because you can only have like whole numbers there. Continuous means that they can take any value on a spectrum. So you can have, any type of decimal there. So things, any type of like measurement in types of like weight, things in centimeters, inches, length, that kind of thing. Those are going to be continuous quantitative variables. Okay. Oh yeah, and just a side note too about categorical and quantitative variables, that categorical variables, they're associated with proportions, and quantitative are associated with means. Just something to remember when you're going through your making those associations there. So categorical, populations, quantitative, means. Okay, so these are different types of quantitative data displays. So I often tell people if they're, confused about these in categorical, to make a list of the two, like a two-way table, list of the quantitative and those, and then a list of the categorical and those, to kind of see the difference between them. So we have our box plot, histogram, dot plot, and scatter plot. All of these do show quantitative data, so there is some sort of value associated with them. The box plot is good for looking at different quartiles, trying to find, the middle 50% of your data, your median, maximum, minimum. That it displays that really well. Our histogram, our bars do touch in our quantitative data display of a histogram, and these are good for large data sets because you can, have a bar that's representing like 1 million, but you don't have to put 1 million dots, and that's in comparison to a dot plot where each sample or each variable is being represented by a dot. So those are better for smaller sample sizes because you don't want them to be like super high. You can't really make them look that. And then scatter plot we will talk about a little bit more here. So scatter plot's going to be our two quantitative variables, and it's described in 4 different ways. So we have our direction, so being positive or negative. So if we're looking at this scatter plot for an example, our direction here is going to be negative. This is just as an example. Our form is going to be either it's linear or nonlinear, and in this case it is showing a trend of being linear. So we can choose that. And then strength, weak, moderate, strong. So weak is showing that there's not really a relationship between our variables. The different samples are really spread out. Moderate, it means they're starting to get close together, and strong means that the samples are really close together in their trend. So I'd say, and you can also say, like moderately strong, you can kind of be in the middle of them. So I'd say this one's pretty strong though, because it does have, the dots are really close together. And then outliers are just representing basically a sample that you got and a point that's like out of the ordinary, doesn't follow the trend of everything else. So if I were to get something out here, that would be your outlier, which will affect the trend of your data. It's going to go more towards your outlier because it's being affected by that. So it will affect your data if you do include it in that. And once again, remember that our scatter plots are 2 quantitative variables. So it is a quantitative variable data display, but it does have 2 quantitative variables instead of other ones which only have 1. Okay, so for categorical, remember we're talking about labels here and categories. So these are different data displays for that. So a bar graph we do have looks similar to a histogram, but remember the bars do not touch, and this is because different categories can't necessarily like share a line. For histograms, a value can be shared between the two because it's a continuous on the x-axis between whatever values you're using, 0 and whatever. But for categories, you can't share a line between like cat and dog because there's not like a common number there. So that's why we do have spaces between them. And then just remember, I was talking about that, so that's representing just one variable and the frequency of that. And then the other 2 examples on the right there are just talking about if you want to have 2 variables. So they're pretty self-explanatory. You can have the bars stacked upon each other or side by side. And still in those, the bars do not touch in that case, unless they're talking about the same variable. So that's what you can see in the side by side one. But yeah. Okay, and that 2-way table is really just talking about if you have 2 variables, again, 2 categorical variables, and you're trying to find, the common place between each of them. So for that two-way table, you can just look at the intersection between, a label for the row and a label of the column, and that'll tell you the amount that is the common number between those 2. And then you often have your totals on the bottom. You can also have them on the, the right-hand side there for, the amount of males and females. So for example, the amount of females who like basketball, 16, amount of males who like baseball, 15. You just want to find that intersection there. All right, so now if we kind of mix them together, we can have a quantitative variable and a categorical variable. So like a category and then a value along with it. So we can have side-by-side box plots with our, we have our categorical variable here on the x-axis. So, actor, actress, the gender is our categorical variable, and their age is going to be our quantitative variable. So here you're able to compare, medians and maximums and minimums. That's just what we can use a box plot for, or side-by-side box plots. And then dot plots and histograms, remember, those were our quantitative data displays, but if we look at them in terms of groups, that's where we add in that categorical variable. So then each category is going to be, each group is going to be our category of our categorical variable, which is usually represented like here. So location for this example. Okay. All right, so normal distributions is kind of the basis of everything we do in statistics because we want things to be normally distributed so that we can accurately make, inferences about it. So when the notation for normal distributions is n, and then parentheses you have your mean, and then our standard deviation. And so for a standard normal curve, it is n, and then parentheses our mean is 0, and then our standard deviation is 1. And then keep in mind, our entire, between our entire curve, all the area behind this is going to be 1 or 100%, obviously, of the data will be below it. And then these are just examples of z-scores that you find on this graphic. It can be placed anywhere, but that's where your z-scores are on your distribution. And then this is the equation to find a z-score. Sometimes you find it on Minitab or stat key, but in this case, this is how you can find it if you have these values given to you numerically, and you can solve it with this equation. All right, and then when we're talking about quantitative data, we often describe it in terms of shape. So what the data looks like if we were to put it on a distribution. So once again, if we're having a normal distribution and it's symmetrical, it's obviously a mirror image on either side. So this means that our mean is equal to our median, which is equal to our mode. So that makes sense because remember, our mean is going to be our average. So that's if you add everything up and divide it by the total that you have. Our median is going to be, directly center of all of our samples. And then our mode is the most common occurring one. So obviously, as you can see here, this is going to, be the highest point on the graph, which is where your mode is. So all of these are the same in it when it's symmetrical. And then skewed to the left, you can see obviously your mode is going to be over here. The most commonly occurring one is going to be there. Your lower values are more spread out, so that's why it's skewed to the left. And then skewed to the right, your mode is going to be down here because this is where your most commonly occurring value is, and it's more spread out to the right, which means it's skewed this way here. All right. All right, so the empirical rule, my favorite thing. I want to get a poster of it on my wall. I love it. Maybe a tattoo. So empirical rule is literally just telling you the percent of the data that lies below the normal curve in terms of how many standard deviations away it is from the mean. So, and this can be for, any different type of curve that you have. That's where you get those z-scores from. So just for an example, if you were to have a normal curve with, let's say, a mean of 6 and then a standard deviation of 4, if we were to go, it's kind of hard to see, if we were to go and show if we were to see where 68% of the data is, so our mean is going to be here at 6, and then so one standard deviation to the right is going to be 6 plus 4, because that's one standard deviation, so this is going to be 10, and then one standard deviation to the left is going to be 2. So that's showing us that 68% of the data lies between plus or minus one standard deviation, so technically between, in this case, 2 and 10. So this is where our confidence intervals come into play, which we'll talk about, but these are just things to remember. This is something that I'll probably just kind of get in your head the more you do it. So, once again, so 68% of the data, which is lying here, and then we have 95% of the data is what we often use between plus or minus 2, and then 99.7 obviously would be 3. So this is 95% of the data, which is where we use our confidence intervals, because we're going to have a lower bound here, and then we're going to have our upper bound up here. And that's where our multiplier of 2 comes from when we're talking about our confidence interval equation. So we'll talk about that later. All right. Okay, so probability, everyone's favorite. So probability is, in general, is just talking about, what's the chance of an event occurring. And it's always between 0 and 1, because we're always talking about, technically between 0 and 100%. So it's either not going to happen at all, which is 0, or it's going to be between almost, it can be up to 1, which is 100% that it's going to occur for sure. So the probability equation in general is just kind of like a proportion. So the number that you have in group A, so that's so if you're trying to find the probability of A, the number that you have in that group, and then divided by the total number that you do have to see what is the chance of that of group A happening there. Risk is going to be just our probability that an event is going to occur in general. So it's literally the same thing as probability. So the risk of an event happening, and it's just talking about the same thing. The number with the outcome divided by the total number. So really the same idea as probability. And keep in mind, though, odds basically, has a similar interpretation, but it's talking about the likelihood of an event happening, so probability, but we are comparing it to the probability of it not happening, which is why our denominator changes down there to the number without the outcome in order for us to make that comparison there. And if you think about it, like I said, our risk is the probability that an event's going to occur. So 1 minus the risk is going to be our probability that it's not going to occur, which is why you can also do your odds equation as risk divided by 1 minus risk, because that's going to be, the event, the likelihood of it happening, so your risk, and then divide it by 1 minus risk, which is the likelihood of it not happening there. So that's where we get those equations from. Okay, yeah, and then residuals, when we're looking at a graph, we're basically looking at here the difference between what the actual, what we predict the y value to be, and then what we actually found. And then this is just the equation for it, for a residual, you know. So for example, if you have a line that you're given with your, this is gonna be your, you know, your predicted line, and let's say for your point of 4, you got that your predicted line says that it's going to be 6. You know, your frequency is going to, or it's going to be 4, 6. That's what you predict to happen at 4. But in reality, maybe you actually got, we can have, maybe you actually got up here, which is like 8. So that's going to be our observed y value. Our predicted is going to be the 6, which is on our prediction line. So then our residual, if we're trying to find that, is going to be the how far between these are going to be, which is, so that's our residual. Talking about how far it is between our observed y value and our predicted one. So our predicted one is always on the line. Our observed one can also be on the line, but if it's not, our residual is going to be that the area, the space between them. If it is on the line, our residual is going to be 0 because there's no difference between the predicted value and the observed value. All right, let's do another review question here. So there are 50 children in a class, 30 girls and 20 boys. If you were to randomly select one child from this class, what are the odds that you would select a girl? So try this one out, and then we will go over it together. Yay, great job, guys. You did a great job on this one. I know probability can be kind of tough, so you guys definitely are understanding this. So remember, our odds is going to be the probability of it happening, so probability of the event, and then divide it by the probability that the event doesn't happen. So technically not the event. so not the outcome. So in this case, the probability of, so we're trying to find the odds that you would select a girl, so that's our event. So the probability that you would select a girl is going to be 30, so the number with the outcome, so which would be the 30 girls, and then divide it by the number without the outcome, which is going to be the 20 boys. Those are going to be all the ones that we do not have, everyone basically as in a girl. And then if we solve this, we're going to get 1.5, so that means basically that for every boy, there's 1.5 girls. Doesn't really make sense, but that's the idea is about odds. So we're going to have 1.5 to 1 because we're talking about the odds of selecting a girl. So our first one is going to be, you know, the odds of getting the girl, and then in terms of if we had one boy. So, and you can check your answer and see if it's logical, you know, because D wouldn't make sense in terms of the fact that we have more girls than boys. So, you know, our first number, if we're talking about the odds that you're going to select a girl, our first number is going to be talking about that, you know, chance that you get the girl, and then in terms of to the second one, which is going to be boys. So there's more girls than boys, so our first number does have to be bigger in this case. So our answer will be C there. So good job. All right, so just a review of the 5-number summary. So we have the 5-number summary of heart rates of 350 Penn State students, probably much higher at this moment for finals, but it's okay. So we have 60, 75, 81, 89, and 105. So which percentage that's listed below of students reported had a heart rate of at least 89 beats per minute? So try this one, and then we will go over it together. Yay, great job. So when I'm trying to figure out something like a 5-number summary, I like to draw a box plot because it has a really good representation of all of that. So remember a box plot in general, if we're just looking at what a general idea of it is, we're going to have our minimum down here, our maximum up here, and then our Q1, first quartile, Q2, which is also equal to our median, and then Q3. So if we were to draw out the 5-number summary in terms of this specific context, oops, let me undo that. Oh, I undid the whole thing. Okay, in terms of this problem, if we were to go ahead and label this, because these are in order, so our minimum is going to be 60, maximum is 105. And then if we were to put the other ones in order here, we're going to have 75, 81 as our median, our Q2, and then 89. Oops, 89. So this question is trying to get at what, you know, percentage of students reported a heart rate of at least 89. So we're trying to find out, this is kind of like the percentile. So we're trying to figure out the percent of students basically that had this, at least this heart rate, which means at least 89% for that. So in this case, so if we go to 89% here, we want to find the percent at or below this in this term. So at this case, we have 89%, and then we are going to go ahead, if we shade all the down here that they had at least 89, we're going to have D 75% because that's showing us them having at least 89 in that case. So yeah, our answer is D, so great job. All right. Okay. Okay, so let's try another one, and then we'll move on to lesson 4. So try finding the z-score corresponding with a raw score of 206 from a normal distribution with a mean of 187 and a variance of 49. So try this one out, and we will go over it together. Okay, so this one's tricky, so get ready. You're gonna be like, oh, Anne-Marie, why'd you do that to me? So let's remember that our equation to find a z-score is going to be our x minus x bar, so our sample, then divide it by s. So remember, variance is equal to our sample, our sample standard deviation squared. So our denominator, to find this, we do have to take the square root of 49 to get our s, which is going to be 7. So we want to make sure then that to do this equation, we're going to have z and then equals our x, which is 206, so that's our raw score, and then minus 187, which is the sample that we got, and then divide by our square root of 49, which is our variance. So then our s is going to be 7. So we actually end up getting about 2.71. So if you think about it, this makes sense, because on a if we were to draw out a normal curve, we would have our mean here of 187, and then the raw score that we got is 206. So that'll be up here. So we want to find out how many standard deviations out from this it is. So if our standard deviation is 7, then that makes sense, because we would be going out about 3 standard deviations, so about 21, which is why we move up to here. So this is corresponding just with a normal curve. If we were to have our normal one of mean equal 0, and then for 206, it just corresponds with our z-score of 2.71. So does everyone understand why we did that one? And don't hate me because it was a little tricky, but you always need one of those where it's like, oh, attention. So yes. Yay! Okay, please let me know if it doesn't make sense. Of course. Thanks for participating. You guys are great. You're doing a great job. Yay. All right. Let's keep going. Thanks for hanging in. You guys are doing great. We have 3 more chapters left, and 5 and 6 are clumped together. So yay. Let's do some confidence intervals. Oh, great. I'm glad the examples are helping. Definitely. And like I said, check the other YouTube videos for the specific chapters, and those will have even more examples on there for you guys to try out. And then you can pause and rewind and whatnot and listen to me talk. Just, that's so soothing about statistics. We all love it. So yay. All right, so let's continue here. So confidence intervals, if we're just talking about confidence intervals in general, like to define them, it's going to be our range computed using our sample statistic. And then we're making that inference, remember, about our population. So we are going to have a lower bound and upper bound. So it's going to be a range. And obviously, like I said, and then the like general equation that we do use for a confidence interval is going to be our point estimate. So this is either going to be p hat or x bar, so our sample. And then remember, like I said, we use our samples to make inferences about our parameter. And then plus or minus our multiplier, which is often 2 if we're talking about a 95% confidence interval. But as you guys know, we do sometimes use different ones depending on the percent confidence interval. And then our standard error. So you'll just either be given that or compute that. And then keep in mind, as our sample size increases, our confidence interval becomes more narrow. So basically it's smaller, which makes sense because, we always want to have a larger sample size. So if you increase that sample size, that means that you can be more confident that the population parameter is within a smaller range. So you don't have to make it really large to make an inference about that population. You can make it more narrow because you had a larger sample, a larger representation to make a inference about that there. But yeah, yay. All right. Yeah, I guess I can do that. Yeah, I've never. Yeah, I have to ask because I don't know if they're like materials, but yeah, definitely. I mean, the one thing. I mean, the PowerPoints will be like on the video, so it'd probably be like the same thing. If you know what I mean, like you'll be going through it the same way that you would go through a PowerPoint. Does that make sense? Like that, like it would be the same thing. You would just like pause it in between. But I can ask and get back to you on that. If I can, I'll send it out. But yeah, I'll see what's up with that. So yeah, anything to help. Okay. Hopefully you guys are having fun. Love stat. Peace, love stat. Okay, so talking about our standard error. Remember, which is our standard deviation of our sampling distribution. And when we're talking about, remember, we made this comparison between our categorical variable and our proportion. These are the related, between our type of variable and then if we're talking about a proportion or a mean. And then a single quantitative variable, quantitative and mean are going to be the connected, or those two that are related there. And then our standard error does have an inverse relationship with sample size. So that means, as our sample size increases, that our standard error is going to decrease. And this makes sense in terms of the fact that our standard error, is kind of saying like how much we're going to kind of accept as being an error in our whatever, if we're talking about a confidence interval or anything. So we obviously want that to be smaller. And like I said, always want to have a large sample size in order to, to be more of a representative sample. So if we have that large sample size, we're going to have a less kind of area of getting an error. So yeah. Oh, and keep in mind the fact that if a sampling distribution is constructed from using data from the population and it's, representative, then we are going to have, our mean, our center of the distribution, of the sampling distribution is going to be approximately equal to the population, which is why we want it to be representative and to be that. So that's where we find that out. So that's just showing that, that's why we can make inferences about the population, because we're finding a sample that has a similar, if not the same, center to it there. All right. Okay, so after we get our 95% confidence interval, we always want to kind of say, like, what does this even mean? Definitely important to keep in mind because, statistics is very applicable, even if you guys are not feeling it, that it is. I do a lot of research, and trust me, this happens in real life, and it does, it's out there, I promise. But so after we find that confidence interval, if you are talking about, things that are actually in context, to interpret it, we're going to have, you always start off with, we are, Penn State, just kidding, we are 95% confident that the population, so remember we're making an inference. So we had our sample, and we made the confidence interval, and we're making the inference based upon that sample, that we're making inference about the population. So that's why we say we are 95% confident that the population, and then remember proportion if we're talking about categorical variables, and it's between 0 and 1 often, and then the mean can also be that, but it's often not. It's usually like whole numbers or larger than 1. So our proportion for categorical or mean in question, or quantitative, is going to be between our lower bound and our upper bound. So those are the two values that we found for our from our sample. And then, yeah, so there's just an example of our lower bound and upper bound that you would calculate there after you get that confidence interval. All right. Okay, so so bootstrapping methods for a 95% confidence interval. So when we talk about bootstrapping, we are going to be taking those samples with replacement. So for normal simple random samples, you take a random sample from your population, and then you just take another one. You keep taking them until you get as many as you wanted, but you don't replace the sample that you already got. So for bootstrapping, we often use this if we have a smaller sample size, where if we took a sample, or a smaller population, because if you took a sample out and you could maybe only get, like 10 samples out of it, because if you keep taking them out and not replacing it, your population is going to, get smaller and smaller for the amount that you have to take out of it. So that's when we often use these. So our standard error method is going to be the one that we use when our sampling distribution is approximately normal. So if this is true, we can use the standard error method, and that's basically what we do every time we use that confidence interval equation of the point estimate plus or minus 2 times, our for a 95% confidence interval, 2 times our standard error. So that's what we've been talking about, and but you do have to use that, or you do have to have an approximately normal sampling distribution for that. And then for our percentile method, that you can use no matter what the shape of the distribution is, because there's always going to be between 0 and 100 between, for the distribution, you're always going to have the lowest, your minimum and your maximum, and then whatever percent of the data in between. So that's why you can use the percentile method for that. So yeah, bootstrapping, yay. All right, let's do a review question. So, okay, in a random sample of 100 dogs, 58% of them have brown fur. Construct a 95% confidence interval for the proportion of all dogs with brown fur. So I gave you the standard error of p hat, so you don't have to go ahead and calculate that. So try this one out, and we will go over it together then. Okay, great job, everyone. I thought about that when I saw you put that answer. I was like, probably had an extra 0 there because definitely understand the concept. So, but great job. Thanks for participating, guys. You guys are doing a great job. So, if we remember our equation for perfect, good job. So, our equation for a confidence interval, we're going to have our point estimate. Plus or minus our multiplier, and we're talking about a 95% confidence interval, so that's going to be 2 for a 95% confidence interval. And then times our standard error here. So in this case, our point estimate, we're talking about p-hat because we are talking about a categorical variable. And let me write categorical, I don't mean cats, we're talking about dogs, but so this is talking about a categorical variable, and then obviously, this is going to be a proportion here, 0.58 as our sample proportion. So if we were to plug all of this in, we're going to have 0.58 plus or minus our standard deviation, or excuse me, of our multiplier of 2, and then times our standard error of 0.087. And then if we go ahead and solve this out in the end, we're going to end up getting a lower bound and upper bound of about 0.406 and then to 0.754. So that's our that's the confidence interval that we get. And then just to go a little bit further into it, and Brian did a great job with no, you can definitely use you can use 1.96. This is, so we often round, technically that is the z-score for a 95% confidence interval, but we often just round it to 2, just for, that's just something that we often do in statistics. So that's, you can use the 1.96, and it's because it's so close, it's not going to make your answer any different, really, not any different, but very small. So, but thank you, Brian. You did a great job with giving us that percent of our, that's going to be represented actually by, to show our interpretation of this. So we can say that we're 95% confident that the proportion of all dogs with brown fur is between about 41% and about 75%, if we were to interpret this confidence interval that we just got here. So amazing job. You guys are geniuses. All right, so let's actually do that. Let's do some more practice with interpreting confidence intervals. So data from a representative sample of 507 adults who exercise regularly were used to bootstrap a 95% confidence interval of the mean wrist diameter in centimeters in the population of all adults who exercise regularly. So I went ahead and give you that Minitab Express output on the right there of this is your distribution, your sampling distribution. Remember, this is bootstrapping, so there is with replacement here. So go ahead and interpret this confidence interval based upon the information that I gave you from this Minitab here. Output here. So you can put this, in terms of a sentence like we showed on the last one. So how we would interpret this in the context of the problem. So go ahead and try this one out. There's a list of all the of like the different multipliers for a 95% confidence interval. I don't think it would be 2.5 though, because for a 95% confidence interval, it's 2. And then if it's 90, you're going to be going in more. So you're getting closer to 0. So it would be less than, it would be less than your 2. So it would be probably like I think it's 1.67. I don't remember. I honestly keep a list of the different or the z-score and the percent of that. So, but yeah, it should be less than 2 because you're getting narrower, so you're getting closer to 0 from your 2 standard deviations out for 95%. 90% is going to be smaller, a lesser amount of the data. So it's going to be less than 2. I'm not sure of the exact number, but you can literally Google it. You can literally say, z-score for a 95% or for a 90% confidence interval. Does that answer your question? You're welcome. Great question. Okay, good. And you guys are definitely doing a great job with, that is okay. Girl, I'm tired too. I walked into my other job tonight and everyone was like, "Are you okay?" I was like, "Yes, I'll be okay." we all got this, guys. Don't you worry. It's only temporary. But so yeah, great job. If we were to interpret this, I had a student one time saying that the way that we interpret confidence intervals is Penn State's way of putting the "we are" chant into your head because we have to keep saying this. So maybe that's what we're doing, but that's not my job. But I know we can do it. The last week of finals, boom. That's okay, Maria. Yes, you're totally fine. So I'm glad you could join us. So yeah, to interpret this, we are 95% confident that, and then we want to talk about whatever, like Jenny did a good job of talking about, we want to make sure we remember the variable that we're talking about, so that the mean wrist diameter, something we're, very interesting, wrist diameter of the population of all adults who, let me write this, in the population of all adults who exercise regularly, regularly is between so we have 10.4602 centimeters, and sorry, I'm running out of room, and about 10.66217 centimeters. Hopefully you guys can read that. So that is our final answer there. So question for the test: what will be safe to use a z-star for 95% confidence? You can use either of them. Honestly, often we just use 2 just because it makes sense in terms of, remember, for our empirical rule, that our we say that 95% of the data lies between plus or minus 2 standard deviations. So it also makes more sense conceptually that way. And yes, of course, yeah. So that's why we use that 2 multiplier often. But yes, great question. Like I said, you're very welcome. Thanks for asking. Yeah, it's very they're so close that it doesn't really matter. So yeah, all right. And then, so yeah, to go over how we got this. So remember, we always start out with, we are whatever percent confidence interval. So in this case, 95% confident that, and we want to talk about then the population mean or the population proportion that we're talking about. And in this case, we're talking about the mean. So we say that and we're talking about risk diameter, that's our variable. So the mean risk diameter of the population. So we're talking about the mean of the population. And then of the actual, what our population was made up of, like who was it? The population of all adults who exercise regularly. So that's our next part. And then is between, and you want to basically go down, and you see on this mini tab output, if you look at the different, we literally have the 95% confidence interval written down here. So you can just use that as for your interpretation. So you have between these 2 values. Does that make sense how we came to that conclusion? Awesome. All right, cool. Great job, everyone. Oh my God, what did I do? Oh my God. Hold on, I totally just speaker. I just made my screen do some stuff. Oh my God. A moment. I'm done. We got this. Oh, hallelujah. We back and we better. Okay. I am a mess. Okay. Let's see. Now I gotta get my chat back up. Okay. Yay. Great job, everyone. Okay. So moving on. Last 2 lessons for this part. So I always split up the review for the first half of the semester and the second half, because I don't think any of us have the stamina to do all 12 chapters in one night. So yeah, let's do 5 and 6 for hypothesis testing. This kind of, I know, right? Oh, can't talk about statistics for that long. I would be dreaming about it. Sometimes I have dreams about my sessions that I forget to come to them or something, but whew, nightmare. But so these 2 chapters were really setting the basis for everything really that we did for the rest of the semester. You saw the trend of, whenever we were doing tests about different types of variables, we were always doing hypothesis tests for them. So definitely this was, if you don't understand this chapter, if you're having trouble in the other chapters, I might want to, start back here to make sure that you understand the basis of hypothesis testing, so that you can continue to do the more complicated sessions that we have later. So our null hypothesis is going to be talking about the fact that we don't think there's any change. We always assume that this is true, and we're always going to have an equal sign here, because we're always assuming that there's no change, which would mean that our either our population proportion or our population mean is equal to 0, or excuse me, is just equal to whatever the value you think it is with no change. And then our alternative hypothesis is never going to have an equal sign. We're always going to have some sort of inequality here, so we have less than, not equal to, and then our greater than. So this is just talking about that we think there's some sort of change going on here. And basically, when we do our hypothesis test, we're trying to prove if we think that this, if, we can reject the null, say that we think there is some sort of change, or if we're going to stay with our assumption that there's no change. So we always assume that our null is true, no matter what from the get-go. Get-go. It's a funny word. Okay. Okay, so for hypothesis testing, what we find out is we want to decide if something's statistically significant. So this is saying, and the definition of a p-value, a lot of people tell me, that it's very confusing. And I personally, when I took this class, I thought it was a little bit confusing to just by the definition itself. So I think about, you want to make sure that you understand a p-value is a probability. But when it says like, or more than extreme than that, we're talking about, farther than what we got. So if we're talking about, for example, let me get something going here. If we're talking about, a right-tailed test, and you get this is going to be your test statistic. So you have your test statistic here, and your p-value is going to be, and then if, like I said, if this is a right-tailed test, so our probability that, it's greater than whatever your value is. Your p-value is the shaded area here because it's more extreme, and in this term, extreme. In this case, we're talking about a right-tailed test, so greater than, so more extreme would be to the right, and that's our p-value there. And then of the what we found was randomly obtained from the population, which is our test statistic. And then if we had like p is less than our value, still one-tailed test, but we're going to have our test statistic and then our p-value is to the left. And then for two-tailed, it's just going to be, it's really small, but it's going to be on either side because you do have these two test statistics here. So more extreme is going to be on either side there. So we make these conclusions in terms of how our p-value is associated with alpha. So our alpha is our significance level. We'll talk about in a second that this is also equal to the probability of getting a type 1 error. And we often send it at 0.05. If you're not given the alpha level, assume it's 0.05. So yeah, we have our p-value. If it is less than alpha, we are going to show that's saying that there's an actual difference in the population. We're making that inference. So that's going to means that we're in favor of the alternative, because remember, this is saying that there's a change. Our null was saying that there's no change. So you always want your p-value to be small because that's basically saying that there's a small probability that what you got was not true. You had to like go farther out basically. So yeah, that's that. Okay, so interpreting a p-value, like what I just talked about, you have the second bullet is what we just talked about. If we have our p-value being less than alpha, it is statistically significant. We're going to reject that null hypothesis in favor of the alternative, saying we think there's some sort of change. If our p-value is greater than that, basically means that we're going to keep that assumption that the null is true, that there's no change, so we're going to fail to reject the null. The language is a little weird, but say it slowly. Sometimes I have to kind of like, say it and write it out to make it make sense. So basically, if you have a big p-value, if it's greater than your alpha level, often, which is 0.055%, then you're going to stick to that assumption that our null hypothesis is still true in that case. Okay, and then when you reject the outcome, when you reject the outcome, okay, you either, so if you reject the null hypothesis, then the outcome is going to be, you mean like a positive value? So not always, excuse me. So when you're rejecting the null, you're just concluding that you think there's some sort of change. So it doesn't, it depends on the context of the problem if it's, a positive or negative number that you were using in your hypotheses for the value. But I see what you're saying because you are p-value greater or, less than alpha. Because also in this case, if our p-value is greater than alpha, technically, so our alpha is often, 0.05, like we've been talking about. So this means that, our p-value greater than that is going to be basically anything that's above, 0.05. So that's gonna, well, actually, that'll definitely be positive. But if our p-value is less than alpha, it's also going to be positive because probabilities go between 0 and 1. You're never really going to have a negative p-value. But so yeah, our p-value is going to be less than alpha, so it's going to be anything less than 0.05 if that's our alpha level. So still positive. They're both going to be positive. It just depends on the relationship to alpha. So p-value is going to be less than 5%, closer to 0 to reject it, and then farther away from 0 for failing to reject it. So great question. Definitely thinking. All right. Okay, so errors, boo. We don't want these, but they happen. Everybody makes mistakes. TBT, Hannah Montana. So errors in decision making, we have a type 1 and a type 2 error. So type 1, like I said, is our alpha level. It's the same thing. Our alpha level is representing that. It's basically saying, what we're going to accept, the probability that we're going to accept that much probability of making an error. So we're accepting a 5% probability of making a type 1 error. So remember, that is going to be rejecting our null when the null was actually true. So we're basically saying that we think there's a change, but there's not. So type 1 error. Type 2 error is different in terms of saying that we're failing to reject the null when the null is actually false. So failing to reject the null, saying that we think there's no change when actually there is a change. So that's a type 2 error. We do denote that by beta. And these are just different terms we use, false positive for type 1, false negative for type 2. As you can see, I love color coding everything. So hopefully that, is helping some people. I know some people are visual. Other people are like, I care less, could be black and white. But so make sure you're paying attention to that, just so you understand my PowerPoint's a little bit better. So yeah, this is just kind of a two-way table to show you, what decision you make and then what is actually true when you find out. And then if you either made a correct decision or had an error here. And then I just have over here on the side, power we'll talk about, but that's going to be your 1 minus beta. So your 1 minus the probability of a type 2 error is your power. People often ask, is a type 1 error more dangerous? Is a type 2 error more dangerous? It depends. It really depends on the context. So often in medical studies, a type 1 error is more dangerous because that means that you can be giving, patients that like ineffective treatments that aren't helping them. So that means, that they can have negative consequences. So rejecting the null when it's actually true. So you think that there's a change and they're getting better, but there's actually no change. So that's, a little bit more serious. But, there are cases where type 2 is more dangerous or serious. So failing to reject saying that there's no change when there actually is a change going on. So that can be things like if you're talking about like lead in water or something, you're saying that, oh, there's no change, where there's not like a poisonous amount of lead in the water, but in reality there is. So that's when like a type 2 error can be more negative there. Oop, oh, I'm still have my little pen on. Okay, so like I said, power is going to be our probability of rejecting a false null hypothesis. So another way to say it, and you'll realize I say things in a bunch of different ways because it clicks in people's heads in different language. So if you have a different way that you like different vocabulary that you use, feel free to share that because it might help someone else too. So our power is our probability of rejecting that false null. So making a correct claim that there's a change. Our power is, if you think about, our type 2 error is making an error, obviously. So our power is going to be, if we do 1 minus our probability of making a type 2 error, that's going to be a correct claim that we made. So making a correct claim that there's some sort of change. So being in favor of the alternative and there actually is a change in the population. And it's inversely related to the probability of making a type 2 error, obviously, because you're just, you're taking 1 minus beta. So everything else is going to be your power in terms of that. So So yeah, if you increase your sample size, you are decreasing your standard error. Remember, just a review about that. But then you're also increasing your alpha level because you're going to accept a higher probability of getting that type 1 error. But overall, for power, that's the main idea. We're talking about type 2 errors here, which remember is beta. I kind of want to get a beta fish, but someone told me they kill each other. So, but I want them to have a friend, you know, so I don't know. Anyway. Okay, so let's do a review problem. I think we have 2 left. Okay, so in a two-tailed hypothesis about a population mean with a sample size of 100 and alpha being 0.05, the rejection region would be where? So here, and you can see I'm using 1.96 here. So that's totally okay. I could have put these as 2 as well. So just an example here. So go ahead and try this one out, and then we will go over it together. Wow, amazing. Superstars. You guys are doing great. So definitely our answer is C here. So if we look at this, so if our alpha level is 0.05, that's our probability, remember, of a type 1 error. So it kind of looks like a spaceship. So we're having a two-tailed test here. So that means that our area our rejection region of a type 1 error is going to be here, so more extreme on either side. So it has to be equal to 5%. So this is going to be 0.025. So 2.5%, then also on this side, 0.025. And then since we have 5% out here, that means that our center is going to be our 95%, because that's obviously the rest of it that equals, this is going to be technically 1 minus 0.05, which is going to be equal to 0.95. So 95%. And then if you remember our empirical rule, plus or minus about 1.96 or 2. Like I said, I could have wrote it the other way too. Used 2 as my number. So, and this is from our empirical rule, our favorite, my favorite. So yeah, that's how we found that out. So, and then since it's a two-tailed test, keep in mind that's why we have less than our 1.96 and then greater than our 1.96, because we are talking about both sides of that rejection region. So great job. You guys are doing great. You're definitely prepared for the final. All right, one last question. You can do it. Okay, so which of the following symbols can be used when writing a null and alternative hypothesis? So this is making sure you understand how to write those and use the correct symbols here. So try this one out. Woohoo! Amazing. Great job, as you've been doing. So our answer is E here. because remember, these two symbols here are how we represent our population. So obviously this is our proportion, this is our mean. And then when we're writing our null and alternative, they're always going to be in terms of our population because we're making inferences from our sample about our population. So we use our sample to make those inferences. So when we're writing our null and alternative, our null can either be p equals something or mu equals something. Remember, always has to have an equal sign there, and then our alternative is the same thing, except you have to use one of these inequalities for that. But you're still going to use, our population. So either, or mu for all of these to show that. So yeah, answer is E. Great job. Wow, you guys are geniuses. Okay, so like I said, you can go ahead onto the YouTube channel. The link is also on the notes page of the STAT website to check them out. And like I said, there's reviews for every single chapter. There's 2 reviews for each, a Thursday and a Sunday session that you can go over with review questions in there and a little bit more in-depth review there. Our next group review will be tomorrow for the next half, well, the final half of the semester. So, oh, great. I'm glad it was helpful. Yay. Thanks for coming by. But yeah, like I said, the second half of our stuff will be tomorrow. So stop by. Don't leave me alone. No, I'm just kidding. If you want to. So yeah, great. And like I said, if you haven't already put your email into the chat box, go ahead and do that for me. That would be great. And let me know if you guys have any questions, but I'm sure you're probably petered out. But so am I. But let me know if you need anything. But yeah, have a great night if you guys are good to go.